the more recent Soyuz crews have been taking 6-hour trips to the International Space Station. This one's taking 2 days, and that's to test out the variety of upgrades that have been added to the newly modified Soyuz vehicle. This includes thrusters, debris shielding, power, and digital video, as well as many other things. But what makes this Soyuz so different from other previous models? A few weeks ago, my colleague Rob Navias sat down with Mark Bowman, the chief engineer of the Soyuz Branch of the Astronaut Office here at the Johnson Space Center, to find out. And he asked Bowman to begin by explaining the goals of the Russian designers had in mind when they set out to improve this spacecraft. Let's take a look.
They stated two major reasons for performing the modifications. The first is to increase the reliability of the spacecraft, and the second is to enhance performance and technical specifications. There were a lot of changes. The first is a structural change. They added additional shielding for micrometeorite and orbital debris to the habitation module. And the intent of this is to increase what we in space parlance call the probability of non-penetration. In other words, to reduce the chance that a micrometeorite or some piece of orbital debris would actually punch a hole through the spacecraft. The second change is a modification to the electrical power system to increase the reserves of power. The first thing they did was to add a fifth battery assembly to the spacecraft. Each battery assembly consists of a prime battery and a backup battery. So by adding a fifth unit, that's a 20% increase in the energy storage capacity on the spacecraft. And to provide the power that go into those batteries, there are solar arrays on the spacecraft, and they added some additional surface area of the photoelectric cells on the solar arrays, which increased surface area by a little over a square meter of area. And they used additional or modern photoelectric cells on those arrays to increase the efficiency by about 2%. So that helps to increase the power reserves on the spacecraft. In addition, they changed the telemetry system, the radio system that sends telemetry down to the ground and receives commands from the ground in the spacecraft, to go to a much more modern system, what they're calling an integrated command and telemetry system. This makes use of the new Russian Luch satellites, which are analogous to our tracking and data relay satellites, and will greatly increase the amount of coverage that the communications systems on the spacecraft. So ground controllers would be able to send commands. As you know now, they can only command to the spacecraft for about a maximum of 20 minutes per orbit. And that's when they happen to be in an orbit that goes over a Russian ground station. Once this system is fully up and running and tested, they'll be able to send commands for at least 45% to perhaps 80 or 90% of an orbital coverage. Also as part of that YKTS system, they've transitioned to an S-band system. They removed the old antennas that supported the old radio system and replaced those with 4 omnidirectional antennas that provide access to the spacecraft from all of the Russian ground sites. And additionally, they added a phased array antenna that will point at the Luch satellites, which are in geosynchronous orbit. So a phased array antenna allows them to point more precisely to get communication with those satellites. They also improved the communication system, the VHF communications radios in the descent module, which the crew members used for voice communications with the ground. The YKTS system includes a backup capability that will eventually enable them to have voice communications in addition to VHF, but that's not functional yet on this first spacecraft. But the improvements to the VHF radios in the descent module provide a lot of additional safety to the crew members, because they've added global positioning satellite receiver on the hatch of the spacecraft. So once the parachutes have opened during reentry, they start taking data from a GPS, which tells the spacecraft where it's located. Then the radio system also has a new transponder that sends then that location to the COSPAR and SARSAT rescue satellite systems. It's a universal system that's used all over the world. And this will allow the search and rescue crews to quickly locate a spacecraft in the event, say, of bad weather or a ballistic entry. So it greatly improves the reliability. The other thing they did was change the Kurs rendezvous radar system, which has been used for many years on the Soyuz. The new Kurs includes much upgraded avionics, modernized electronic systems, new antennas. They have actually reduced the antenna footprint on the spacecraft. As you know, you've seen the iconic photo looking out of the blister of the Soyuz as they approach the ISS, and you can see an antenna that's rotating in the field of view. That is a Coors antenna that is no longer needed. It was very complicated mechanically, and also it had to be retracted prior to docking with the space station so that it didn't come in contact with station structure. The new Coors allows them to put a small phased array antenna on a fixed bracket that doesn't have to be retracted. It weighs less, uses less power, it's much less complicated. Also, you might recollect a boom on the aft end of the spacecraft that had two Coors antennas. That boom has been removed, and the antenna has been placed on fixed locations on the spacecraft body. So that simplifies the spacecraft and reduces weight. All in all, the Coors modifications reduced the weight of the Coors system by about 25 kilograms and takes about 30% less volume, and it uses about 24% less power. So pluses all the way around. Another thing that they did to this spacecraft is change the approach and attitude control thrusters, which in Russian we call the DPO thrusters, that are used to maneuver the spacecraft and change its orientation. The previous DPO thrusters, there were 28 of them. 16 of them were large thrusters of about 13 kilograms of thrust, and 12 of them were small thrusters, about 3 kilograms in thrust. The new configuration uses 28 all large thrusters. And it provides a lot of redundancy now by positioning 14 pairs of thrusters around the spacecraft so that there's a redundant thruster for every other thruster, and they are operated on separate, completely redundant manifolds for propellant. So if one thruster fails, the other thruster immediately, in its pair, immediately picks up and assumes control. You recall in December when the 45 Soyuz approached and they had a false indication of a thruster failing, that required the crew members to manually take over and dock to the space station. With the new thruster configuration, that would not have been a problem. A failure of one thruster just transitions to the thruster on the backup manifold. The other advantage of the new thruster configuration is that on the aft end of the spacecraft, there are 8 thrusters instead of 4. So if during, say, a deorbit burn, for example, if the main engine were to fail, now you have 4 large thrusters to be able to perform your deorbit burn instead of only 4. And so that provides additional level of redundancy as well.
How have all these modifications been tested, Mark?
Well, the testing has been comprehensive and extensive. Most or many of the modifications have already flown on previous versions of the Soyuz. Even though they were TMA-M vehicles, they one by one implemented some of the modifications. They tested the redundant drive motors on the docking system. They tested the Coors system. So they've been tested on both Progress and Soyuz vehicles. And then finally, the last 2 Progresses, 62P and 63P, have included all of the modifications comprehensively so that they'll have 2 positive flights and positive test results on Progress vehicles, giving them great confidence that the Soyuz will be fine.
This launch will send Kate Rubins and her crewmates on a deliberate 2-day rendezvous instead of the more common 4-orbit 6-hour rendezvous that we've become accustomed to. Why?
Well, the main reason for going to a 34-orbit rendezvous on this flight is to provide additional time to test the new systems. Going to 34 orbit gives them lots of time to test the new unified or integrated command and telemetry system. It gives them a chance to do some flying quality assessments with the new thruster configuration, and it gives them a chance to test communications using the new Luch satellites as well as the ground systems, which have been upgraded to work with the S-band telemetry.